So this equation right here is actually a conservation of energy equation. Notice that in the previous line we had said net work is change in pressure, negative change in pressure, times this differential volume. And then we said this is kinetic energy times volume. Oh, this isn't really kinetic energy though. This is kinetic energy per volume times volume, because density, well, density is, check it out, density is mass divided by volume. So this is kinetic energy per volume multiplied by volume. Then when we cancel out volume, we get kinetic energy per volume. Over here, this must be some other kind of energy per volume. So pressure is a kind of energy per volume. And I'd like you to think about what it could possibly be. Think about pumping up a tire or, well, things like that, popping a balloon. Think about what kind of energy a pressure actually is if you've got something under pressure. There are actually cars, golf carts mostly, that you put a big tank of compressed air in the back and then you sip off of that sucker to make the car go around. It was considered as a major means of transportation, but it has some technical issues like explosions. And the tank is usually pretty heavy too, because it's got to be strong enough so that it doesn't explode. So let's keep moving through. I'd like to consider, instead of this situation here where we had fluid getting compressed, not compressed, but getting into a narrower area and therefore a higher speed, I'd like you to consider instead, wait a second, is it clear to you that this equation tells me how, this equation here tells me how speed changes when pressure changes, or how pressure changes when speed changes. So this is a very powerful equation, and we'll investigate its full results later on. But right now, I want you to consider this situation. Now I'm going to have fluid moving upward. So this is my y-axis, and I'm going to start it at, let's say here's 0. Here's y1, and then I'm going to have it move up to y2. So here's a little tube of fluid, and that tube is going to stay at the same diameter all the time, and it's going to turn here, and this will be the outflow of the tube. Same area, same diameter, nothing interesting except that our tube has risen. So what do you think is going to happen to the speed? Based on diarrhea, we know that the same speed must be present here as is present here. So there has to be the same amount of mass going through each section, so we know that those speeds are the same. But the pressure, well, the pressure could be different, but the speed's going to be the same at least. Down here, we'll define this to be, what? What happened? Okay, this is supposed to be y1. This is where we're starting, and that's where we're ending up. And 0 will have to be somewhere down here. I don't even care about 0, but just saying we're at some starting height, and then we're at some finishing height. Let's figure out what happens. So I'd like to propose that the pressure could be a little bit different. I guess, yeah, we'd probably have to be careful about this. This pressure here, this is pressure 1 down at the bottom, and this is pressure 2 right here. This pressure is pressure 1 minus, it'll be less? I think it will. You know this rho GH thing we've been carrying around a little bit? Well, here's rho, and here's G, and here's this height difference. H is y2 minus y1. So that's the positive height, but we're saying the pressure up top is less than the pressure down at the bottom. Usually we'd have pressure, but let me just write that down here. Typically, we're looking at this equation. Pressure at the bottom is pressure at the top plus rho GH. I'm kind of just using the opposite of that statement right here. Pressure at the top is pressure at the bottom minus rho GH. And notice how I've written the height as y2 minus y1. So then I want to consider the work done by the pressure. Pressure is going to be doing work here, and that's work 1 plus work 2, and the difference in work from the pressure is simply P1 minus P2 times that differential volume, that small chunk of volume, just as we saw in the previous video. So you can check that to figure out where I'm getting this. But gravity is also doing work. Is gravity doing positive or negative work as the stuff goes up? Let's figure that out. Gravity's work is, well, I'm going to put a minus sign right here, and I'm going to say it's negative that chunk of mass that goes up times baby g times y2 minus y1. So this says that gravity is doing negative work. Y2 is bigger than y1, and gravity acts down while the thing goes up. I suppose that's fair then. So m, I don't like to write m. You know I don't like to write m. So I'm going to write rho times delta v, and then I'm going to put a baby g here, and then I'm going to try to squeeze in y2 minus y1, and then I'll close my parentheses just barely. Then, I want you to consider what's happening with the velocities. There's no change, right? So I'll write but, and then I'll say that the change in kinetic energy equals 0. Ooh, change in kinetic energy has something to do with work, right? So then I can say work net equals, and I'm going to put a little parentheses here, equals 0. Let's just remember that the net work is going to be equal to 0. But let's write it out. It's the work done by the pressure plus the work done by gravity, and they must cancel out. The result of that is that I've got P1 minus P2, I'm taking this equation and plugging it in right here, times delta V, and then I have to, I gotta get this gravity equation in here, and then I'm supposed to add the work done by, where's my minus sign? Oh, dang it! Look at this. See this minus sign right here? That minus sign is supposed to be right there. Also, you have to have that minus sign right there. That's a big, big mistake of mine. Then I need to subtract rho times delta V times baby G times Y2 minus Y1. All right, do I have the work done by gravity? It's a negative number, and I'm adding it to the work done by the pressure. It's a positive number, and the whole dang thing is equal to sweet nothing. You see what I can cancel? Ding, ding. This is very, very powerful. We've canceled the volume again. And I'm going to compare like terms. I'm going to get everything that's got a P1, everything that's got a 1 on one side, and I'm going to try to get rid of these minus signs and all this nonsense over here. So I'm going to say that we get P1 plus. Now it's going to be plus because I've got negative sign here and negative sign here, and I'm keeping it on the left side, so those cancel out. P1 plus rho times g times y1 equals, now on the right side, P2 is going to be positive, P2 is positive, and over here I've got a negative times a positive, but I'm moving it over to the right side, so it's going to be positive again, plus rho times g times y2. Beautiful equation. Let's put that in a box, give you a little flower pot, if you want. Here we go. Flower pot. I'll put this one on its head. It's okay, you can still turn it over and put a flower in there. Sure you can. Generally though, this equation tells me how pressure changes as height changes. It seems like pressure goes down as height goes up, which is reasonable because if I take my hose from my house and stand it straight up, the water won't come out very much. Very reasonable, right? But I want you to take this equation and combine it with, oh shoot, where's that other one? I got it. Let's combine it with this equation to make a super equation to rule them all. Here it is. My new equation in summary, I get to say that P1 plus, this is I guess I should just be honest with you. Pressure is a kind of energy divided by volume. This is a potential energy divided by volume. It's the potential energy per unit volume for pressure right there. I guess if I have more volume with the same pressure, then I've got a greater amount of energy. That makes sense. A small tank at 100 psi doesn't have much energy, but a big tank at 100 psi has a much more energy. So you go to Lowe's, you want to buy something that holds a whole bunch of energy, you got to buy one of those tanks that's bigger than you are. All right, so I'm going to put this in summary, one equation to rule them all. I'm going to have P1 plus 1/2 rho times V1 squared, that's the speed, plus rho times g times y1 equals P2 plus 1/2 rho times V2 square. Keep it coming. Plus rho times G times Y2. This is Bernoulli's equation. Mr. Wojak is fond of saying that when you are in the shower, you are never alone because Bernoulli is there with you. You can think a lot about Bernoulli's equation. This has incredible implications and you can do lots of cool problems with it. But notice it's not on your physics sheet in this form. Check your cardstock sheet and see how it's different. But this is potential energy. This is kinetic energy, and this is, what kind of energy is this? It looks like MGH, right? This must be another form of potential energy. Good luck. Play around with it. Make sure you follow everything that I've done. Is a kind of energy per volume. And I'd like you to think about what it could possibly be. Think about pumping up a tire. So this equation right here is actually a conservation of energy equation. Notice that in the previous line we had said net work is change in pressure, negative change in pressure, times this differential volume. So this is kinetic energy per volume multiplied by volume. Then when we cancel out volume, we get kinetic energy per volume. Over here, this must be some other kind of energy per volume. So pressure, and then we said this is kinetic energy times volume. Oh, this isn't really kinetic energy though. This is kinetic energy per volume times volume because density, well, density is, check it out, density is mass divided by volume, or, things like that, popping a balloon. Think about what kind of energy a pressure actually is if you've got something under pressure. There are actually cars, golf carts mostly, that you put a big tank of compressed air in the back and then